In this video, we will discuss the force, mass, acceleration approach to solving kinetics problems involving particles. When a particle of mass m is subjected to one or more forces, it will accelerate if the forces are not balanced. The resultant force vector is the sum of all individual force vectors and is written as sum f. The particle will accelerate in the direction of the resultant force vector. The mass of the object is a constant of proportionality relating the resultant force vector and the acceleration vector. Sum f equals ma is called the equation of motion or Newton's second law of motion. Using this equation, if we know the forces acting on the particle, we can find the acceleration of the particle. And once we know the acceleration, we can, in principle, find a particle's velocity and position through the kinematic relationships and integration. Alternatively, if we know the motion of the particle, we can determine the forces acting on it. A brief word of caution. For the time being, we will assume that we are observing the particle from an inertial reference frame, that is, a reference frame that is not rotating or accelerating. Although the Earth is rotating about its axis and is undergoing centripetal acceleration while traveling around the Sun, ignoring the motion of the Earth leads to negligible error in many, but not all, engineering applications. If we want to account for the movement of the Earth, we would have to introduce fictitious forces into the equation of motion. If the particle moves along a straight line, we say it is undergoing rectilinear motion. In these cases, it is usually more convenient to use a rectangular coordinate system. Let's take a closer look at the resultant force vector. In the rectangular coordinate system, this vector has x, y, and z components. The x component of the resultant force vector, sum fx, is the sum of the x components of the individual force vectors. In the example shown here, sum fx is equal to the x component of f1 plus the x component of f2 plus the x component of f3. Similarly, the y component of the resultant force vector is equal to the y component of f1 plus the y component of f2 plus the y component of f3. And the z component of the resultant force vector is equal to the z component of f1 plus the z component of f2 plus the z component of f3. The acceleration vector also has three components, ax, ay, and az. The equation of motion can be broken into three scalar equations, multiplying the mass and acceleration on the right-hand side and equating the terms in the x direction, y direction, and z direction. We now have three scalar equations of motion. The sum of the x components of the forces is equal to the mass times the x component of the acceleration. The sum of the y components of the forces is equal to the mass times the y component of the acceleration. And the sum of the z components of the forces is equal to the mass times the z component of the acceleration. The magnitude of the resultant force vector and acceleration vector is the square root of the sum of the components squared. Note that if the particle is restricted to move in just the xy plane, sum fz and az are both 0. We are free to choose the orientation of our axes. If we choose the x-axis so that it is parallel with the line of motion, then the acceleration in the y and z directions becomes 0, and the components of the resultant force vector in the y and z directions are 0 as well. This may greatly simplify the problem. When a particle moves along a curved path, we say that it undergoes curvilinear motion. Although we may use a rectangular coordinate system for this type of motion, often it is more convenient to use a pathline coordinate system with normal and tangential coordinates. In the pathline coordinate system, the t-coordinate is positive in the direction of motion and the n-coordinate is positive toward the center of curvature. We previously saw that the resultant force vector can be split into its components. If motion occurs in a two-dimensional plane, as shown here, in the rectangular coordinate system, one component of the resultant force vector points in the x direction and the other component points in the y direction. In the image on the top right, the x component would have a positive value since it points in the positive direction of x, while the y component would have a negative value since it points in the negative direction of y. When using the pathline coordinate system, one component of the resultant force vector points in the t direction and the other component points in the n direction. In the image on the bottom right, the t coordinate would have a negative value since it points in the negative direction of t, while the n component would have a positive value since it points in the positive direction of n. We can expand the equation of motion into its components using pathline coordinates and multiply the acceleration components by mass. Then equating the tangential components and normal components, we have expressions for the equations of motion in the pathline coordinate system. Recall that the magnitude of the acceleration in the t direction is the time derivative of the speed, v dot, and the magnitude of the acceleration in the n direction is v squared divided by the local radius of curvature rho. The speed is equal to rho times beta dot, which is the local angular velocity about the center of curvature. The magnitude of the resultant force vector and acceleration vectors is the square root of the sum of the components squared. This leads us to the force, mass, acceleration approach to solving kinetics problems. First, on a free body diagram, identify the forces acting on the particle and choose a set of coordinate axes. Your choice of coordinate system and axis orientation may greatly simplify the problem. Next, relate the forces acting on the particle to the acceleration the particle experiences by using the equations of motion. And finally, if you wish to find the velocity or position of a particle, you can relate its acceleration to those quantities through kinematic relationships.